Let's look at the following problem associated with conservation of momentum. Puck B, that is this one here, which rests on surface of ice, is struck by puck A, which was originally moving with a speed of 50 meters per second in the direction shown. After collision, A is deflected 30 degrees from its original direction, so it moves like that. B moves 45 degrees with the original direction of A, so that is the direction for puck B after the collision. The pucks have the same mass, so that's an important information. A, find the speed of these pucks after collision, namely find U and V. What fraction of the original kinetic energy of A is dissipated during the collision? So this is a classic example of conservation of momentum. This is the initial state and that is the final state. So conservation of momentum states if there is no external force acting on these objects, and we know there aren't any external forces because the motion takes place on the surface of ice, so you can neglect completely the effect of friction, for example. So the conservation of a linear momentum says the initial momentum of the system is the same as the final momentum of the system. So let's see what the initial momentum of the system is. Now this is supposed to be the vector equation here because momentum is a vector quantity. The initial momentum of the system is only contributed by A because B is at rest, so no linear momentum from B. Now we shall take this direction to be the x direction and that to be the y direction. So the initial momentum of A is its mass, let's call it m, times its initial velocity. Now it is 50 meters per second in a rightward direction, so it's 50 times I hat, where I hat is a unit vector along the positive x-axis. As we have said earlier, there is no contribution to initial momentum from puck B. Now let's look at the final state, where both the objects are moving. So let's look at A first. The mass is m. What is the velocity? Well, it's moving on xy plane according to our setup of the coordinate system. So the x component of the velocity is quite simply u cosine 30 degrees I hat, because the x component of u is that way. The y component is going that way. Now we are just looking at the blue object, the puck A. So the y component of its velocity is u sine 30 degrees j hat, where j hat is a unit vector along the positive y direction. So this term represents the momentum of puck A after collision. To this, we shall add the final momentum of puck B, namely the momentum of puck B after collision. So its mass is also m because we are told that they have the same mass. The final velocity, of course, has two components, x component of that v going rightward and the y component going downward. So the x component is quite simply a v cosine 45 degrees I hat. The y component is minus v sine 45 degrees j hat. We note that this minus sign is due to the fact that the y component of B's velocity after collision is heading downward. So there we have it. The initial momentum of the system equals the final momentum of the system. We note both sides have m, so they go away. So I'm going to rewrite this equation on a new slide and solve it there. And there it is. U is at the speed of puck A after collision and V is the speed of puck B after collision. Now let's proceed to solve it. So let's write down the x component of the above equation. So the left hand side has only the x component, so 50 equals this plus that, so u cosine 30. Cosine 30 is square root 3 over 2 plus v cosine 45 is 1 over square root 2. Now let's look at the y equation. On the left hand side, there is no j hat term, so that is 0. The right-hand side, you only have this minus that. So u sine 30 is half minus v sine 45, which is also 1 over square root 2. So two equations, two unknowns, and you can solve them simultaneously. Let's solve u first by taking the x equation and add that to the y equation. You see that the second term goes away, and you get 50 equals u square root 3 over 2 plus half. And you can solve for u. When you do that, you get 36.6 meter per second. So that represents the speed of puck A after collision. Now putting this solution into this equation, you can get v. And when you do that, you get v to be 25.9 meter per second. And that is the speed of puck B after collision. So there we have it. For part A, u is 36.6 meter per second and v is 25.9 meter per second. Now let's do part B. What fraction of the original kinetic energy of A is dissipated during the collision? To do that, let's write down the initial kinetic energy of the system. And that is given by the initial kinetic energy of A only, because B was stationary. So that is half times the mass of A times the square of the speed of A, which will be 1,250 m joules. Now the final kinetic energy of the system, and it's given by the kinetic energy of A after the collision, which is half times m times u squared. We know u is 36.6, so 36.6 squared, plus the final kinetic energy of puck B, which is half times its mass times v squared, and we know v is 25.9 squared, and that will be 1,005.2 m joules. So the fraction of this original kinetic energy that is dissipated during the collision is calculated by the following way. Let's call that fraction delta K. So it's given by the magnitude of that change over the original kinetic energy. So that means using these two numbers, your delta K is Kf minus Ki, so that is 1005.2 minus 1250. Remember, m is just the mass, and it's a common term, over Ki is 1250 m. So m goes away, and this fraction will be 0.196, or in percentage 19.6%. So 19.6% of the original kinetic energy of A is dissipated during the collision. And that solves the problem. Thank you for watching.